Here we need to find out the moment of inertia of a solid cone about a slant height. Let us begin. Let us suppose the parameters of the solid cone are m, r and h. Now if we can manage to find out the moment of inertia about a parallel axis passing through the center and that for a ring, then we can start from there and find our final answer. So let us first try to find out the moment of inertia about this axis which is passing through the center. But initially let's do it for a ring, because with the help of a ring we can move on to a disk, then we can move on to the shifted axis by parallel axis theorem, and then we can integrate. So let us break down this problem into steps. So the first step is to find out that for a ring. Now if you still have a doubt in this, you can check my previous video. I'll be using the result straight away. For the case of a ring, that comes out to be mr square 1 minus sine square theta divided by 2. Now first we'll move on to the disk. So step number 2, we will go from this to the disk. So for that we'll have to integrate and take elemental rings. So let us do that. So instead of capital M, now I will have elemental m, so that will be m by pi r square to pi r dr. So my capital M is done, multiplied by, now the radius is small r, multiplied by 1 minus sine square theta by 2. Now obviously this integration is over the radius because we are moving from a ring to a disk. So this is 0 to capital R. Pi goes away. This is r cube dr. We all know that very well. That will be r4 by 4. So we get mr square by 2, 1 minus sine square theta divided by 2. Now we are done for a disk. So from this we have moved on to a disk. Now we need to move on by shifting the axis. So step number 3, we'll apply the parallel axis theorem so that we can move on to the desired axis. So therefore the moment of inertia for that disk will be the previous term plus some extra term, which is the mass of the body multiplied by the separation between the axes. Now here these two axes, which are of course parallel, will have a separation of r cos theta squared. So therefore this looks something like this. Plus cosine square theta. Now we'll move on to our final step. So basically now we need to move on from the disk to the solid cone. So let us suppose this is our symmetric axis, the z. This angle is our theta. So therefore my final answer will be integral. Now for the mass, I will first write down the density of the solid cone multiplied by the elemental volume of the disk. So that will be pi radius squared multiplied by the thickness, which we can easily notice will be dz. Now the radius of an elemental disk will be z tan theta. So we are done with the mass. Now the radius again with the square, we already know that, z tan theta whole square multiplied by this same thing. Now this doesn't change because theta still remains the same. So half sine square theta plus cos square theta, where obviously we already know what is tan theta, sine theta or cos theta, as we can look from the geometry. For example, tan theta is nothing but r by h. Similarly, we can find sine theta and cos theta. Now the integration is obviously over z, that is our variable, and that goes from 0 to capital H. When you do this simple integration, you get the final answer. That comes out to be 3 by 20 mr square 6h square plus r square upon h square plus r square. This is our final answer. I hope this video was helpful in some way. Thanks for watching.